Hey guys, my name is Farzan. Everybody calls me Farza. So this title, it's really broad. Deep convolutional nets and video games. I'm not going to go over like a deep tutorial about deep learning or specifics about like how everything works. But what I'm going to do today is I'm going to make sure you guys understand how you can apply this this idea to video games. Because we see deep learning. If you guys know about deep learning, it's been used in some really interesting ways in the real world. You can, like for example, computer vision, natural language processing. Every time you use Siri, that's deep learning. So this thing is being used for a lot of real-world tasks. But I wanted to use it for something a little weirder, video games, something I'm into. So let's do it. So the first thing I want to go through is why I think so a lot of people might think that applying this to video games is kind of useless. And I think that's because they don't really see what it could do. So that's what I'm going to be going over before I talk about some stuff. So a bit about me. I work at Visor.gg. We are a video game analytics company. We are out of Y Combinator, and I'm a machine learning and computer vision engineer over there. Essentially, so you can go to our website, Visor.gg. But the funny thing is our website says nothing about what we actually do. So should fix that. And essentially what we do at a very high level is you give us your video, we analyze it, we make you better gamers. And it's all via the video. We don't use any API. We don't do anything. We literally just we parse your gameplay. And right now we're doing Overwatch and Fortnite. So hopefully that's Fortnite players in their audience. Before I was doing this stuff, I was doing self-driving car stuff. So my task, my problem that was given to me when I was doing research was given a camera pointing out of a dashboard. Can we learn how to steer a car from just one camera looking at the road? So that was what my research focused on. I wrote a paper on it, did really good. And yeah, so over here, this little red dot is what my model predicts. The only input is the image. So all the model gets is this video, and you get the black dot behind it is the right answer. So that's what how the car was actually being steered. That's what my model predicts. So it's pretty good. Very little area. I feel like if you used my thing, you probably wouldn't die. But yeah, it's funny. My professor was always like, before I graduated, I was gonna put it in my own car. My professor stopped me. He said, "I know you got good results, bro, but I don't think it's a good idea." So let's talk a little bit about what the point of all this is. So I'm gonna go back to my professor. He was this really old dude, 80 years old. And every time I bring up video games, he just feel like you're wasting your time. It's not a real problem. So let's just talk about why I think that it's kind of cool. So the first thing, video games provide a controlled environment, playground to test new ideas. By that I mean video games are this really complex thing. It's like a really complex problem that we as humans created. If you guys have heard, think of an Elon Musk tweet or something, yeah. OpenAI, they beat a pro player in a video game called Dota. Dota is this really complex game. And a lot of people were like, oh, that's cool, you beat a pro player at a game, so what's the point? And the thing is, in this whole field of AI, we don't really know where we're going. People think that there's this trajectory that we're for sure on. But for the most part, no one really knows what we're doing. And we're kind of just doing stuff that's cool at the moment. So at this point in time, it was really interesting to beat a pro player at a video game, a very complex problem to actually do. So the idea being that if you could beat a pro player at a very complex task, like a video game, could you do some other simpler task? Maybe like doing a very simple surgery? Who knows? The point is if you don't actually try it out and you don't actually do it, then who knows? But yeah, video games are such a complicated environment to test like the limits of how much AI can, the limits of how far AI can go. And that's why we've been obsessed with solving things like chess and Go, and now larger video games. So second thing is solving problems in games can give us the basis to solve real-world problems. So like I said, just because when you beat a pro player in a video game as a bot, it's more than just that. You have now realized how to essentially, you have trained some AI to play a very complex game and understand a lot of the environment and actually play it properly and beat someone at it. So the idea being that if you can do it in a game, you can apply them to even more complex problems in the real world. Something I worked on was Grand Theft Auto. This is Grand Theft Auto right here. This is not real. It's a very, very realistic video game. I made a self-driving car in Grand Theft Auto. And I used the data, used the research I did in Grand Theft Auto to then apply it to a real-world problem, a real self-driving car. So I first tested my ideas in Grand Theft Auto, and then I actually put it in an actual, in a real car. And the third thing is it's just cool. I feel like you shouldn't do things just because they have like a purpose or because you can make money off it. It's just cool. Just do it because it's kind of cool. For example, you guys might know about this very popular algorithm called GANs in deep learning. It's this thing where you give it an input, and it'll create stuff automatically. So here, we give the model an input. The bird is red and brown with a stubby beak, and this is what it outputs. So it literally thought on its own. And when the guy first made this, there's a story. He was just messing around in his lab. It wasn't anything like important. He just thought it was cool. And now it's become one of the biggest things in AI as of recent. Yeah, just do things because they're cool. All right, so now let's talk a little bit about what my tool, my project is a little. It's all about League of Legends. How many of you guys know about League of Legends? Oh my God, wow, okay. Cool, a lot of people know League of Legends. So League of Legends is right now, I think it's the most played game in the world. Fortnite might be beating it. But as of right now, the data shows that League of Legends is the most played game in the world. And essentially, all you have to know for the presentation is your team has 5 players, 5 unique characters, and the enemy team has 5 unique characters. And you guys just got to kill each other and destroy each other's bases, and you win the game. And something that we're going to be focusing on today is this thing at the very bottom, this thing right here. This is called a mini-map. It gives us the position of every single player on the map at every point in time. So for example, this is a player right here, this guy right here, his name's Graves. And we can see how he moves around the map and what he's doing. So I think I skipped something. Yeah, skip this. Yeah, so this is a little weird. I was supposed to go over this slide first, so let's just do this one. Imagine for a moment that you were the coach of a soccer team, and you could actually figure out where all your players were on the field at any point in time. So as you can see here, this is a video, and we draw little boxes around the players. So we actually know where everybody is all the time. So as a coach, you can imagine this is really helpful information, right? Knowing where all your players are at the same time. You can find patterns in how your players were positioned when a goal was scored, or how your players were positioned when they got scored on. And you can become a better team like that through the data. And that same concept now is being applied. We're going to apply that same concept in a game. League of Legends is a huge world. This whole thing here is huge. Like when it would take a player to walk from here to the other side at least 3 minutes. So we can almost compare it to a soccer field, where players have a lot of room to move around, and that means there's a lot of room for error as well. So what we can do is, and remember, the whole goal of League of Legends is you got to kill your enemies. That's just how it works. So for example, we could actually track players on the minimap and tell you where you're dying a lot, where the enemies are dying a lot, where create a heat map of where a lot of people are dying, and maybe find patterns and how we can actually play the game better. So, yeah, who cares about this stuff? What if? So I'm talking to you guys about doing better analysis on video games through deep learning. So I think it's important to understand who even cares. What's the point? These guys do. These guys are pro players from North America, Korea, and Europe. They get paid a lot of money to play this game professionally, and they care about heavy analysis and getting better at the game at the data level, actually. So you as a normal casual player may not care, but these guys definitely do. And the cool part is this is a very lucrative industry. Many people are throwing a lot of dollars into this place, and all these guys want better analytics for their teams. And that's what this thing I'm trying to show you guys today does. Also, this is just an example. This was the League of Legends World Finals last year. It's massive. A lot of people it's they play this thing in stadiums. That was Beijing. Oh, it disappeared. It broke. A saved. Don't look at my tabs, guys. It's not there. Yeah, I don't know what I actually don't know what just happened. My fat phone. What's up? Nice. Yeah, my bad. Okay. So yeah, a lot of people watch this thing, and it matters. That's what I was getting at. Cool. So let's talk about the problem one more time for people who might have not gotten it the first time. We want to track each of these players on the map. Each of these little circles is a player, and we want to track them according to their icon. We want to know where everybody was and who they were. So I want to know that this player, this guy right here, his name's Graves. I want to know that Graves was at position 10, 20 on the minimap, for example, right? We want to be able to do that from just a video. So our input is a video. That's all we get. We have to figure this out. And this is a bit of a problem because there's over 130 unique characters. So that's already making the problem a lot. So there could be 100. This guy could be potentially 130 people. And we got to figure out who he is. Also, there's this big problem of occlusion, basically. So over here in the middle, you can see that icons can go over each other like that. And that makes the task even harder for us. So that's another problem. And it needs to be fast. So my idea when I made this thing was I wanted to give it to like actual pro players, and I wanted them to be able to use it. So it'd be really lame if this algorithm took like 2 hours to run on a single game. It should run in real time or faster. That's how I wanted it to be done. So yeah, we need all these things. And if there's any questions about the problem, just let me know. Cool. But yeah, essentially track people on the minimap and tell me who they are from just a video. So then this is this brings my tool into account. So what Deep League does is it takes a video into as input, and it'll output to you a bounding box and the actual name of the character along with a confidence value. So here we see it says, I am 99% sure this is Graves, and it makes a little bounding box around him. And it does that for all 10 players on the map. And as you can see here, occlusion is not a huge problem because it's deep learning, and it does pretty well, even when people are like really on top of each other. And this is called Deep League. This is it's something I made. It's a neural net I trained. It's a command line interface, and it's a data set, which I'll be getting to more. But yeah, most of the rest of the talk is almost like a little story about how I actually figured this out, because it was not easy. So there's a whole blog post about this thing. It went pretty viral on Reddit and Medium. So if you want to actually check it out and read it after this, or really like go in depth. Like, I really go in depth about how I did everything. This talk sort of skims the surface, but yeah, if you want to check it out, there it is. But yeah, when I did release this thing, everybody went pretty wild because being able to know where everybody is on the map is so, like, imagine if you had it for soccer, right? If you just knew where everybody was all the time and could just aggregate data across everyone's games, you would know like, oh, Ronaldo really likes this spot, or some other player really likes this spot, and he always scores goals there, and we can stop him. I did the same thing, but in the world of gaming. So not everybody here may be familiar with deep learning, but I don't want to alienate the audience. So I'm going to do the fastest deep learning tutorial you've ever seen. Let's say we want to make a simple self-driving. We want to make like a self-driving car. Sort of. We want to have an input as an image, and we want to output a steering angle. So given this image, how should the steering angle be positioned in terms of like, should it be like 20 degrees, 18 degrees, or how should it be done? So let's talk about this. This is your input, and we go through what's called this magical Amazon box. All right, I won't explain this thing yet. I'm going to explain it later, but it's just a box. It's magical. Let's just vibe with that for now. And this outputs to us 25.6 degrees, for example. But the right answer is 47.6 degrees. So what we do is we get really mad at Amazon box, and we say, you are so wrong. Fix yourself. And Amazon box slowly gets better. And we keep on doing this. We do it again. We say, oh, Amazon box outputs 4.6 degrees, but the right answer is 8.6. So it gets better slowly over time. And the idea is you keep feeding this magical box data, and it's going to get better over time. Because it literally learns by example. That's all. There's more deep learning, but in the end, it's just learning by example. Yeah. Yeah, it does. It would. So that's another thing. That's actually, but for now, I think so. This would work if it was just like you would crash, right? It wouldn't be a real self-driving car, but it could tell you approximately how to steer a car. Because speed doesn't really matter that much when it comes to how to steer a car. Yeah, it probably does. That's why I'm saying this is not real. We're using a magical Amazon box, bro. This is not real. All right. So do we even need deep learning for this? A lot of people told me you don't need deep learning. You could just use normal computer vision. There's no need to throw this very sophisticated algorithm at this simple problem. So here's the mini map again. You're probably tired of it by now. But it's 295 pixels by 295 pixels. That's 86,000 pixels in this image. Let's say we're trying to track this little guy right here, this circle right here. This guy's name is Echo. That's how he looks. That's how his image looks. That actual image is 11 by 11 pixels. That's 121 pixels. So you're essentially trying to look for 121 pixels in this 86,000 pixel array, right? And what ends up happening is, so people told me, oh, just take that image and just look for them across the entire image. Literally take that tiny image and just slide it across and look for that guy. And the reason this doesn't work is because it's too small. And what ends up happening is false positives just start popping up everywhere. Like, this thing is kind of blue, he's kind of blue, this must be Echo, right? But that's not how it works. This is not that character. This is just another blue thing. It's a very naive method. And secondly, it doesn't work well with occlusion. Remember, these guys can be on top of each other fighting and stuff. So the second they start getting occluded, this method completely messes up. So we needed something a little more sophisticated. And then I started thinking to myself, could we apply object detection to this problem? And for those who are not familiar with object detection, it means give me an image, and I will tell you where stuff is. I will literally draw boxes and tell you what that thing is. So here it says, here I give it an image, and it says, yo, that's a dog, that's a bicycle, that's a car. And object detection is really, it's gotten really good. Like over here, it picks up this bike, despite this dog standing right in front of it. And yeah, object detection is insane. So yeah, I was working object detection at the time with my research. And I was like, yo, let's just see if this works. And I went on my journey. So then here's the problem now. Our input is this thing right here, the mini-map. And our output is a set of bounding boxes. So remember how we made the self-driving car, and we just taught it example by example? We're going to apply the same concept here. The input is an image. The output is going to be a set of bounding boxes. And the idea is that it will learn where all 10 characters are on the mini-map at the same time, but through example. So for example, over here, it says that's Echo, that second thing in the array, and Echo is right here. So we give it the right answer in the end. And we hope that it learns. And this is essentially, I'm going to go more into how object detection actually works. But very high level, we're predicting bounding boxes. Our input is an image. OK, cool. Seems like a good idea. That means we need data now. So it's all cool to have a nice idea, but you need the data to actually power some model. There's no API you can hit for this thing. Nothing. There's no public data set. That'd be nice. There's no way to access in-game memory. So I was trying to hack the game and trying to figure out where everything was, but I got banned for that. And I have a lot of friends who work at that company, and they said they couldn't help me, because I was fiddling with in-game. I was trying to hook in the DLLs that actually made the game work, and you're gonna get banned. I don't want to manually label all the frames. Remember how we had the mini-map? I would have to actually go in and draw like a box around every character and tell you who that character was for a lot of frames, like thousands of frames. I didn't want to do that. I'm also poor, so I don't want to have to pay anyone either. It's kind of lame. So yeah, it's over. What do we do? At this point, most people would probably quit. And I actually did quit for like a solid 2 weeks. I put it on hold. I'm like, all right, this is not gonna work. But yeah, I slowly got a little more creative. And this is where it starts getting really weird. So yeah. So there's this thing. So remember how I said that pro players play this game? They play it for a living. Essentially, so when pro players actually play the game, they're playing somewhere else, like in China or Korea or America. They're playing somewhere else, but all their games are streamed. So anyone can just go in and watch the stream. And that stream is on riotgames.com. Riot Games made League of Legends. They made that game. So one day I was watching the stream on riotgames.com. And remember, this is a live stream. This is a live game happening. And I was just fiddling around in the inspector tools on Chrome, me and a buddy. And what we found is that when a stream happens, when pro players start playing, a WebSocket opens up on riotgames.com. And what we did was we went into the WebSocket and we looked at what it was actually outputting, right? And what we found was actually, it was crazy. So the WebSocket was giving us data for the actual game that was happening live. So for example, let's say a game is happening live, and we look at the WebSocket. The WebSocket would literally tell us where everybody was on the map and at what time. And it was all secret. This is literally me just messing around in Chrome DevTools, right? And yeah, and it outputs this thing called, if you guys don't know how WebSockets work, pretty much it opens up, and if someone's there to listen to it, then you can hop in and you can listen to the WebSocket. But if no one's there to listen to it, it is literally just throwing out data into the sky. So I listened to the WebSocket. I was like, all right, buddy, what are you saying? And essentially, a WebSocket throws out frames of data. So this is an example of one frame of data that the WebSocket is throwing out, a big golden frame. And it literally gives us the time in the game and the name of the player who was playing and their position, that y-axis at the bottom. It gives us those very important things. So yeah, problem solved, right, guys? Yeah, so that's cool. So we now know where people are on the map at any time, as long as we're listening to this WebSocket. OK. So now the problem is, remember I said, you have to listen to a WebSocket, or else it just throws data into the sky. So I had to somehow record the WebSocket. And I somehow had to always save its data that it was throwing out. So I did something pretty simple. I made a node script, and I made an EC2 server. I set up an EC2 server. And I had that node script listen to riotgames.com. And I said, every time riotgames.com opens a WebSocket, listen to it, save the data, just save that, and hold it for me. And I let this run for about, I think it was 3 weeks. And yeah, just to go over the process one more time, node script to listen to the WebSocket. Amazon EC2, so it's just always listening. It's always in the cloud. I don't have to mess with my computer. It doesn't restart, and it's always running. And now we just wait. Because remember, the WebSocket only throws out data when a pro match is happening. And pro matches happen like 8 times a week, maybe more. So I had to wait a little while, quite a while. And pretty soon, I say a few weeks, but it was actually a few months. It's a typo. So a few months later, I had data for about 250 games of League of Legends. And this is how it looked. It was just a bunch of JSON files for each game, just like that. But remember, we are trying to make a data set of images. All I had was JSON. I had a bunch of JSON files. I don't have the video from the original games. So I then had to go to YouTube and download each of the 250 games videos manually. And I saved those games. So now what we have are 250 MP4 files that were actual recordings of the game, and 250 JSON files. Each of those JSON files were the actual was what the WebSocket actually output to us. It had the position of the player at every timestamp and the names of the players at every timestamp. So I know it's getting a little complicated, so I try to make it a little simpler here. So now we have, for example, game1.mp4. We go to frame 1 of game1.mp4, and we go to frame 1 of the WebSocket. And we can match these up and know where the players are based off the WebSocket. Just like that. And we had these for 250 games. So for example, game 2, exactly the same. You have a data frame from the WebSocket associated with each actual frame, like RGB frame, input frame. Cool. So now the final step. Remember, so for those familiar with neural nets and deep learning, we can't really pass JSON into a neural net. You could, but you're going to have a bad time. So we needed to actually format the data in a way that made sense. And to a neural net, what makes sense are arrays, simple matrices, simple NumPy arrays. So I took the JSON data, and I converted all the JSON data to NumPy arrays. This is literally what I'm passing to my neural net. Just a set of bounding boxes and positions. For example, 38 here, that 38 could just mean a specific character. So that 38 could mean 38 maps to this guy right here. And he is at this position. That's all that means. And I did this for 250 games, right? Yeah. Now we're done with the data side. This was actually like the worst part of it all. I think getting the data and putting it into a way that is usable for you in an actual problem is one of the hardest parts. So I think anyone could have a model going and ready, but if you don't have the data to feed it in the right way, then it's gonna be bad, guys. Cool. So now we have a bunch of data, and just so people remember how the data looks, I also didn't mention I saved all the data into test, train, and validation sets. So I have a training set, I have a validation set, and I have my final test set, which my neural network never sees, and that's what we actually evaluate our results on. That's a nice GIF. All right. So now we wanted to choose a model. So a lot of people think that when they want to make a model, they make it from complete scratch. And you could do that. You could definitely do that. But the thing is, when something is complicated, when you want to do something as complicated as object detection, you don't really want to manually make your own model. It is, I feel like you'll learn a lot. But the thing is, why not just rip off some PhD student, who's working like 1 year on it, and he was in a lab and he made it perfect. Just look at his work. It's totally fine. There's no shame. So there were 3 really popular object detection algorithms at the time: RCNN, SSD, and YOLO. It's actually called YOLO, by the way. Everybody thinks I'm memeing or something. It's called YOLO, and it stands for you only look once. And the author is really, if you guys don't know this guy, Joseph Redman, Google him. Look at his blog. That guy, he's hilarious. Probably the funniest guy in the computer vision community. And yeah, so these are the 3 very popular algorithms out, like even right now. So I worked with YOLO before, and it was for self-driving car stuff. And I would do this stuff like this. I would detect cars, traffic lights, trucks, and other things on the road. So that's on the right. That's YOLO right there on the right. So this is how it works. Faster RCNN, very, very accurate, extremely accurate, but so slow. SSD, pretty accurate, not really that slow. And YOLO, it's just really fast. It's not the most accurate, but it's extremely fast. It works at like 10 frames per second. I don't remember the exact stat, but it works faster. It works pretty much in real time. And that's why people in self-driving car actually use this algorithm, because it's just so fast and it works in real time. So remember, being fast is something I wanted, and that's why I chose YOLO. And plus I used YOLO before, so that's why I'm going with YOLO. And just a quick rundown of how YOLO works. I give YOLO as input an image. YOLO then breaks it up into this grid like this massive grid. And each little grid cell right here is responsible for predicting a certain number of bounding boxes. So what ends up looking like is this. There's a lot of bounding boxes, right? And then what ends up happening is, let's say we predict dog on the top right of this image. Let's say we say there's a dog right here. What happens is, there's not a dog there, right? So what YOLO says is, there's definitely not a dog there. You are so wrong. And the model will adjust, right? It'll say, OK, this is definitely not a dog. I'm sorry. It won't happen again. And it gets better. That's just how this works. And you keep on doing this over many iterations. And you'll hopefully get a model that is good at object detection. But yeah, this is how YOLO works. And the final output essentially takes all this noise and figures out what is most common. So in this case, most common is this big yellow box right here, and that's a dog. Or that big red box, and that's a bike. Or that big yellow box in the bottom on the top right there, which is a car. And it filters through all the noise and figures out what's most common. And it figures out it's a dog, bicycle, and a car. So I was going to code YOLO from scratch. But the cool thing about YOLO and its creator is he is super open source. So he has all his stuff on C++ online on GitHub. I could have coded it myself. Probably would have taken me like a month. I don't think it'd be that hard, but it's just why do you want to do it? Once again, there's no shame in just using someone else's code. So I use this thing called YAD2K, which is a very popular wrapper for YOLO. And a quick rundown of how YOLO looks and works. So we've been talking about this Amazon box thing right here, right? This is what's actually in the box. This thing called a convolutional neural net, a deep convolutional neural net. And essentially what a deep convolutional neural net does is it learns features for an image. So for example, for the minimap, it might learn to pick up on circles, or it might learn to pick up on certain colors. So over here, you can see that the convolutional neural net is detecting a lot of red or green or lines, straight lines. And it learns these features so it can better predict the final thing, which are bounding boxes. And yeah, I highly recommend if you are interested in YOLO that you actually read the paper. It's pretty funny, and the guy is the actual paper is funny, so that's pretty weird. And it's just really simple. It's a really simple read. Most academic papers are really scary, and they're full of these crazy equations and such, which is fine. But when you're new, you don't want to get scared away. I think YOLO is like a really cool paper to actually start off with. OK, cool. So now what do we got? I, at this point, had about 100,000 images, over 250 games, and 100,000 data points, right? I also had this is YOLO, by the way. So this is the same thing. That's YOLO in picture form. This is YOLO in text form. This is literally what YOLO is. It's just a bunch of convolutional neural nets, a bunch of max pool layers. And it is huge. It is 50 million parameters. There are people who, that is massive. That's all I can say about that. And all I had was my 2012 MacBook Pro. So this is probably not going to work, right, guys? 100,000 images, 50 million parameters. I actually started training this on my MacBook Pro, and it was taking about a day per epoch. So epoch is one run of your training set. So it would take me about 50 days for it to finish on my MacBook Pro. So we need something else. We can't. It's not gonna cut it. I also didn't have money at the time. I was in college. So I'm still pretty poor, but in college it was really bad. I can't just buy a Titan X and do my thing. So yeah. That's essentially what was happening. My MacBook Pro was out of commission. Just a really quick funny story. My brother is also doing research now in deep learning, and he's doing like stuff for the military. And he's an undergrad, and him being an undergrad, he ran a really complex model on his MacBook Pro. And his MacBook Pro actually broke. Like, it does not work. It white screens now. And now he knows to not run complicated stuff like that on his poor MacBook Pro. So we need the cloud, for sure. So what I ended up going with is I got this thing called AWS. So yeah, it's just a machine that you can rent out, P3.8x large. And some stuff about it. It has 4 Tesla GPUs, 64 gigabytes, 32 CPUs, 244 gigabytes of RAM, and it costs $12 an hour. So I did not know how long this thing would take to train. So yeah, let's just go from there. Also, Goku, because when I figured out how to use this thing like a year ago, when I first started dealing with cloud computers, I was like, yo, nice. So yeah, way better than training on my MacBook Pro and waiting 50 days. We have this many. So for those who don't know, deep learning works better on a GPU, essentially, for many reasons. Cool. So the next step was to actually train this thing. So when you want to train a neural net and you have this much data and you're dealing with a model this complex, you don't want to just start training every time. You want to start with like this little, you want to start with like 100 data points first. Literally just start with like the dumbest thing. Try to train your model on 100 images. Because what's going to end up happening is you're going to get a lot of errors no matter what. You're going to get a ton of errors. So what I like doing is I like to overfit a small batch of data on my model. So I just know everything's working. Because debugging this stuff is really hard. I'm skipping over a lot of stuff. I debugged this thing for like 2 weeks at one point. So save yourself the trouble and follow this procedure. Just overfit a small portion of your data set and fix all the errors as they come. So you're going to get errors like image dimension, output image, out of memory. This is the biggest one, by the way. Nice. Cool. My friend just messaged me back there. Cool. This is the biggest error here, out of memory. It means you're running out of RAM. So you would think that 244 gigabytes of RAM is enough, right? But man, it's not. So you got to figure. I'll be talking about that in a sec, how I fix that. And there's a bunch of other errors. This was also a big one, out of GPU memory. So what I actually did, so I don't actually know what kind of instance I need for YOLO. What I did was I started with the cheapest one, and I kept going up until I found the one that didn't crash. So I think I think I went through 7 different models. I went through like 7 different things on AWS until I actually found the one that didn't crash. That was fun. I wasted a lot of money on that, by the way. And yeah, so that was another big thing. And yeah, a bunch of CUDA stuff. Installing CUDA used to be a pain. Now it's really easy. Yeah. Cool. So after 50 epochs and training for 2 days and me spending $500 on AWS, I had a trained model. And this model could take as input an image, a whole video, and would output to you where everybody was on the mini map at every timestamp. And you can see it does that. It does it really confidently. Like it is 0.9, like 95% higher or more confident that that it's tracking that's actually the hero, right? And I think it's really interesting on the bottom when things get crazy. It still does a really good job at making sure it gets everyone, because those guys are really fighting on top of each other there. And yeah. So some finishing touches. I wanted to release this to the world. So if you make a neural net model, no one's gonna even care about it unless you actually make it nice and usable. So I could have just like got my final model and put it out on GitHub, but no one's gonna care because they don't I don't know how to use this. So I made sure to make this thing really nice. So the first thing I did was I created a really simple command line interface to actually interface with my model, and I use Conda, which is a virtual environment. So literally all you have to do is go to my GitHub, run this command on Linux, and activate, and you're done. And you can actually run my model now. Then to actually run the model, you literally just Python test deep league and then the name of a video file that you actually wanted to process. And I also added, after a lot of people pestered me, YouTube support. So you can actually pass a YouTube video to the model, and it'll work. So yeah, I'll keep going. So yeah, a lot of people started using this thing pretty much immediately. And pro players didn't know how to download their own videos, so they're like, "All right, guys, sure, I'll put YouTube support in." So yeah, now that they got YouTube. And the funny thing is that pro players didn't really use this much. It was mostly their coaches. It was mostly their. So now esports teams have entire data science teams, which is crazy to think about. If you go to like a League of Legends team house, if they don't have a data scientist living in the house, then something's going wrong. So a lot of data scientists started pinging me about this thing. And yeah, so Deep League today, it's used by a lot of large esports organizations. If you guys know like Team Solomon, Cloud9, those guys. It's gotten a lot of developers into AI for esports analytics. So that was my main goal with this thing. I didn't really care about, I sort of cared about solving the problem, but my main goal was I wanted esports analytics to get better. Because it stayed pretty stagnant. People were just always hitting the same API, getting the same data, and pouring out the same dumb average analytics. So I wanted something cooler. And that's what people are doing now. A lot of developers are actually thinking outside the box for once. That's pretty great. It's also used by many players, like casual players. So you can imagine that having this data would be a great cheat, right? So a lot of players made their own cheats, and they're using that right now. And the company's not happy. Because, by the way, this is computer vision. So how can a company know that you're recording your screen? Like, well, what are they going to do? Ban you for recording your screen? So people actually made their own cheats where they record their screen, and it tell them when the enemies were playing a certain way, and when like the enemies were about to kill them, and it warned them, right? So people made that. Totally illegal, but I thought it was kind of cool. Also, it's gotten many like young gamers into deep learning. So like a lot of college students have hit me up, high school students, and they're just like, "Yo, this has actually got me into it, and I'm actually learning more about it." Because I think people like doing this stuff when they relate it back to something they like. So most young people like video games. So a lot of people started getting into deep learning because of this too. And a lot of people have tried beating me, like my algorithm. So this is one guy. He tried, because remember, my data set is completely public. That data set of 100,000 images is on my GitHub. It's 30 gigabytes, and you can download it. So a lot of people tried beating me. And so a lot of people tried, and it didn't work out. This is one guy. He tried like at least 6 times. And also, just like random messages I get. This guy from Google wanted to like figure out how to implement it. This other like random data science student in Italy wanted to learn how to use it for other stuff. So they got really a lot of people like working on this task of doing computer vision on video games. And yeah, all my code and the data set, it's all there. It's actually on the data set's on S3 right now, which I pay for. So if you guys download that, I pay for it. So please don't download it a lot.